Hello, hello, testing. Okay, good. Afternoon to everyone. Afternoon to everyone. Um, so tonight, after the lecture, we have a committee for lecture notes. So we try to write self-content lecture notes. Okay, so that you know what you need to learn or what's the background you need to revise, okay, do revision on, so that you can excel in this course. Okay, we try to make everything rigorous and detailed and clear. Okay, so far we have 6 people like that. Okay, and the other one is about RT tutorial questions. I hope you already start doing it. Okay, otherwise, if you just rely on assignment, you won't learn much. But if you think that I think tutorial question is I already finished all of them. A bit boring. Okay, I want you to try and do extra one. Okay, challenge yourself. Okay, do the those without solution. Okay, if you do it, you can come and discuss with me during the office hour. Okay, in particular, Ping, right? Ping is trying to do that. So if you want, you can work with him together. Okay, yeah, you can work with him together, and then we can try and produce a solution for Arctic. Okay, if possible. If not, just for your own learning is okay also. And the other thing is, please always check your Moodle, check the announcement that I made. So in particular, we have replacement next Tuesday. Okay, next Tuesday morning we have replacement for the what holiday is it? Malaysia Day. What's the holiday before we start? And what day is that? Malaysia Day, huh? Malaysia Day and Prophet Muhammad, what? Something like that. Okay. So we have a replacement for that. And assignment, I think still got 6 person haven't signed, haven't hand in. So if you want to have extension, please message me. Okay, please message me. Okay, until this Friday. Please message me. Otherwise, I'll come after you. So in case you know your friend haven't submitted, please tell your friend to message me. Hey, it's Hong Rui, is Hong Rui here? Where's Hong Rui? Are you ready? You said next lecture, right? You want to show us a non-associative LLC with non-unique first example? Very quick one, no need too long because I also need to do lecture. Just draw us the example and then maybe say a few words. Yes. Yeah, you can draw it here. Here now is your turn. This color. You can use this.
Define a set.
You want use this? Use this one, please. Use it.
then A is identity. If we define B times C is A and C times D is A, then they are not equal.
Yeah.
No.
Something else you say. Thank you. So basically, Hongri produce a set, okay, and then define an LLC. So this is just LLC, there's no requirement for commutative or associative or what. You just tell me when you compose two things, what you get. So the easiest way to record this data is using the multiplicative table. Okay, so she defined that B compose C is A, okay, and then A compose D is D, okay, and then C compose D is A, and then B compose A is B, and then you A priori can let A, B, and D different. Okay, so maybe you can see that there's a hole inside your multiplication table, right? But it doesn't really matter. You can simply fill it in. Okay, yeah. But the main point is you make the LLC not associative. Does it make sense? Okay. I think you come up with this method even before I teach multiplicative table, right? Already. Did you do self-learning yourself or what? No, then how you come up with this tool, multiplicative table? Very natural. Wow, good. Very good, very good. Good, good, good. Good, good. Very good. Thank you, thank you, thank you, Henry. Yeah, so like what I say, mathematics is actually really natural. Okay, you need to think naturally. These two will come out natural one. Too excited, huh? Too excited. Okay, so mathematical two is really a natural things. It's not like 死记硬背, it's not like that. It's not about memorizing. Okay, so in case for example, the arting solution, right? Okay, you say, hey, Kisan, I try one solution. Different or different way with what you have written inside your solution manual. You can come and show me. Okay, I can try and check for you. Okay, if it's how to say really different, then maybe we can try and add it in. Okay. So doing mathematics, you can use different way one. It's not just one way things. Okay, this applies throughout every mathematics question. Okay, don't believe any lecture that tells you that there's only one way to solve it. Okay, that's not like that one. Okay, so be open. Okay, the main thing for mathematics is you have to be open. Okay, be open. That's why we have so many branches. Okay, so before we start, let's do this quiz. Okay, everyone try and show why is this true. What? Yeah, try and do this. Yeah, I give you 2 minutes. Try and verify these. Okay, so let's try verify using a cycle notation first, and then we will check function composition also. So let's do the first one first. Okay, so do we really get a 3 cycle here? Okay, do we really get a 3 cycle here? So where do we start? Really, we can start with any indexes. Okay, we can start with any indexes because if you're gonna get a cycle, no matter where you start, it's still a cycle. Let's start with 1. Okay, so remember that when we take products of cycles, right, we always start from the right. This is equivalent to function composing. You start with right first. Okay, so does this cycle 2, 3 or transposition 2, 3 do anything to 1 or not? No, right? Okay, so we need to go to the next cycle. And then we see that next cycle will send 1 to 2. But is there any more function you're going to compose? No, so you're going to stop at 2. Okay, so now start again the process. Okay, we need to see where 2 goes now. Okay, under these two functions. So first of all, you can see that the right hand side function send 2 to 3. Okay, so where does the 3 go for the next one? It stay the same. Okay, got fixed. So you will stop at 3. Okay, and then can we close it yet or not? Not yet. We need to check also for 3. What happened to 3? Okay, so you can see that on the right hand side, start all over again. The right hand side, where does 3 go? 3 go to 2. Okay, then you should consider where the 2 gets sent for the next one. Where get sent? 1. Okay, so 3 get back to 1. So you finish the cycle, so you close it up. Okay, now? Okay. Again, for the second one, let's repeat again. So any indexes you can start. In particular, I want to start at 1. Okay. So let's see where 1 gets sent to. Okay. So if you start from the right, you see that 1 gets sent to 2. Okay. But does the next one do anything to 2 or not? No. Okay. It gets fixed. So you stop at 2. Okay. So you repeat the process. Where 2 gets sent to. Okay. Start from the right one. Repeat. Where 2 gets sent to? To 1. Okay. And then does the 1 get sent to anywhere else by the next cycle? 3, right? Okay, 3. So how about this 3 here? Is 3 going to go anywhere? No, right? So we're going to stop at 3. Okay, again. So right hand side does nothing to 3. So you need to go to the next transposition. And then you see that 3 gets sent to 1. And then there's no more already. So you're going to stop at. Okay or not? Okay. Is everyone comfortable with this multiplication? Okay. So then we just skip this one. Let's you explain again. So if it is function composition, what do you do? Okay, let's see what do you do. Let's see what happened to function composition here. So let's say we do 2, 3 first, and then we do 1, 2. Okay. Okay. So this kind of swap is normal because due to how we write the function. Due to how we write the function. Okay. So we will do 2, 3 first. So under 2, 3, 1 get fixed. Okay, and then 3 and 2 swap. Okay, and then under 1, 2, 1 and 2 will get swap. Only fix 3. So altogether, what happened to this map? 1 gets sent to 2, 2 gets sent to 3, 3 gets sent to 1. Run up. Yeah. So this is the cycle 1, 2, 3 back to 1. Make sense? Okay, so there's a method 1. So this is a method 1. And this is a method 2. Okay, no? Okay, how about 1, 3 and 1, 2? So what happened? So we do 1, 2 first and then do 1, 3. So we check what happened under this map. What happened to these 3 indexes? So under 1, 2, 1 and 2 will get swapped. And then 3 get fixed. Okay. And then under 1, 3, 2 get fixed. 1 and 3 got swapped. Okay, so altogether, what happened to this function? 1 gets sent to 2, 2 gets sent to 3, 3 gets sent to 1. Does that make sense? Okay, no? So you can see that different way of composition are compose the same thing. Okay. Okay, so similarly, you can check for the third one. Okay. So in last class, right, I also taught you about what? String notation, right? So maybe we quickly go through this string notation here. So how to do string notation? In string notation, right, you always fix the order of your indexes. Okay, so always fix the order of your indexes. So for example, under 2, 3, what happened? You will have a cross, okay, between 2 and 3. Right or not? 2 go to 3, 3 go to 2. But 1 get fixed. Okay. And then under 1, 2, meaning 1 and 2 will get a swap, and then 3 get fixed. Like this. Okay. So can you imagine what happened? It is like we just move, let's say, the map. Okay, I repeat again. So we just move the map going from 2 and 3 to the bottom, and then move the map from 3 to 2 up to keep the order as ascending order. Okay, ascending order when you go down. Okay, so when you want to do string notation, you use the same order of indexes. Okay, but when you do it for function, you care about where the element in the domains go. Okay, this is the difference, but they're really the same. Okay or not? Okay, but if you do the second one, what do you get? You swap 1 and 2 first, correct or not? Okay, and then you keep 3. Okay, and then if you do 1, 3, you will swap 1, 3, and then you keep 2 like that. Okay, is it correct or not? Am I doing something stupid or not? All right. Okay. Yeah. So you can see that these two things is actually equal. So let's say we try and ignore these indexes, we just combine these line together. Okay, just combine because we're composing, right? Okay, what can you see? So you can see that these two pictures are the same. See how I draw this. You see like that. Bit ugly, yeah. The true? Yeah, true. Okay. Why is this two the same, huh? Why is this two the same? From the function viewpoint is the same. Okay, from the function viewpoint is the same. Can you see these two? How are these two pictures the same? Can you imagine anything to make them the same? Sorry? Huh? Yeah. Yeah, right? The start and the end is the same. What happened to the middle? Can you make them the same or not? No. Imagination，发挥你的想象力，怎样让它一样？我让你玩，我现在要让他们一样嘛，我的目标，但看起来很不一样。有没有一种方法让他们一样？Is there any way you can make them the same? Sorry? Stretching. Yes, stretching. Can you imagine that if I stretch this line to here, to the above, and then stretch this crossing below, isn't it they look the same already? Can you imagine or not? Imagine or not? So let me draw it. So can you imagine that I stretch this above, okay, and then I stretch the maybe stretch this guy below. Isn't it the same? So let me redraw this picture. So this is equal to this, and then you do this, then you keep this one. Isn't it the same? Same or not? The first one and the last. Same, right? Okay, so if you stretch the first line here to the top and then stretch the second line here to the bottom, they look the same. Almost the same. Okay, if you stretch more. Okay, so this kind of stretching without breaking the line is called a continuous mapping. Okay, under this continuous mapping, they are the same. And then this is the subject of topology. Okay, if you're interested. Yeah. So under topology, they are the same. Okay, you can do strange. No testing on this one, no worry. I just give you extra info here. Okay. Right. Another thing is, can you observe some formula here or not? Can you observe some formula by this equation here? Okay, imagine this is a random tree cycle. Can you observe some formula here? Let me move this word. Okay, can you observe some formula here? If this is a random tree cycle here, how to break ijk into product of transposition? Okay, maybe you can do it as ij, jk, and then ik times ij, and then equals to jk times ik. Okay, so how you imagine, for example, so for the first one, right, it's like repeat the feeder index if you want to break it. Okay, but the second one, can you imagine a way to remember this formula or not? When you want to move ij, when you want to commute ij with jk, it doesn't commute, right? Because we have proved that most probably function composing is not commutative. Okay, so when you commute ij with jk, what happened? What happened? When you commute ij and jk, if you want to keep ij on the right, then you need to change your jk. How to change your jk? How to change your jk? Since there's a overlap of j here, then the second j here will become an I. Okay, so you commute with an non-trivial effect here. Does that make sense? Okay, okay, but having said this, there's required proof. Okay, they require proof. Okay, but this is how you can remember. Okay, how to commute to transposition. Okay, okay. So let's do a few proof, and then we will justify this line along the way. Okay, we will justify this line along the way. So last time I promised you 3 proof, right? So let's do it now. So the first statement we'll have is let sigma and tau be 2 disjoint cycles. Okay, we still remember what disjoint cycles mean? So you have 2 cycles, but their indexes doesn't overlap. Okay, not equal pairwise. Do you have an example in mind or not? For example, what? Whenever I say let something, you need to have some example in your mind. So what? Any example in your mind? Very easy example. 2 disjoint cycles. 1, 2, and 3, 4. Good, very good. So to learn mathematics, you need to always keep some easy example in your mind. Okay. So then what? What's the statement here? Then they commute. Okay, they commute. Okay, just now doesn't commute. Okay, you can see that 1, 2, 2, 3 they are not disjoint. Okay, but in this case, if they are disjoint, they commute. Okay, if they are disjoint, they commute. So how to prove this? So last time we have computed that 1, 2, 3, 4 equals to 3, 4, 1, 2. We have computed this using function. But how do you show it generally? Okay, so if you want to show it generally, right, for sure, you need to start with n cycles. Okay, potentially 2 different cycles, correct or not? So let's write down the assumption first. So since sigma and tau are disjoint, okay, we need to write down the general form. Okay, we can write down the general form. So we can write sigma as sum I1, I2, up to IK, and tau to be J1, J2, up to JL. Potentially they are different cycle. Maybe K cycle and L cycle. Okay, we just require them to be disjoint, such that what? Such that all the indexes are pairwise disjoints. Okay, so where is in between I, K, and Q. Okay. By the way, it's okay that you use my last year lecture notes to do pre-read, so before the lecture. But after lecture, right, please use the current one because I will update the detail inside. Maybe sometimes, maybe last time there will be some mistake or something that I need to change or add. So please download the latest version to do revision. Okay, but you can use my previous version to see what I'm going to talk next. Okay, yeah. So please download the latest one. And I'll frequently update. Yeah. Okay. So what? Yeah. So what? So what's the key point that made you commute? What's the key point that made you commute? If they are same thing, you mean sigma tau and tau sigma is the same thing? Yeah. How to argue they are the same thing? Okay. And then they are what? Those are what? Those are what? What do you mean? What did you say? I didn't listen to what you said. So do some trick there. Oh, do some trick there. So what kind of trick? So so they are disjoint, right? In particular, meaning what? Meaning what? So what does sigma do to this ji to jl? What does sigma do to j1 to jl? For example, okay, if you don't like ijk, right? You like number more. Let me ask you, okay, 1, 2, what does 1, 2 does to 3 and 4? Nothing, correct or not? What does 3, 4, the transposition 3, 4 did to 1, 2? Also nothing. Okay, so this is the key point here. So what we see here, so not that sigma fixes to ji up to and tau fixes I1, I2 up to ik. So from this fact here, right, we can just deduce that the function commute. Okay. So from here, we strictly straight away deduce that they commute. Does it make sense? Can you see from the example? So if 3, 4 did nothing to 1, 1, 2, what does it mean? No matter what happened to 1, 2, 3, 4 won't change it. So it doesn't matter when you do this 3, 4. Similarly to 1, 2, no matter what you do to 3, 4, 1, 2 won't change it, the transposition. Yeah, so the order doesn't matter. Since I do not believing. What was your question? Your question? No? Question? No? Hey, you have to ask question. Pan Seng is very, was that very cute? Why very cute? Because when I give her 3 examples, then she is very happy already. Make sense. So you are learning this mathematics degree, right? So you need to learn to prove. Okay, anything that makes sense, you need to prove is correct. You know why? Otherwise, this is how the scan start. This is how all scans start. Makes sense at first. And then your money gone. Hey, serious, this is a very serious problem. Seriously, there's a story told by my colleague. There's one SMUM student, okay, get an embassy call from China saying that you do money laundering. Do you know what's money laundering? 洗钱哦，学生洗什么钱嘛？ Okay, money laundering. Okay, that student believe and then pay him. Okay, paying 10,000. Haven't finished yet. Call again. Call again. This time the student don't want to give money already. You know why? No money. Maybe not. It's not because that he think that the embassy people scam him, but that person scolded his father. I'm not sure. During the conversation, scolded his father. Then only then he wake up. It's quite weird, right? You don't do money laundering, but you pay money. But when people scold your parents, you do a different decision. Isn't it weird? Yeah, think about it. This is a real case happen in our society. Okay, think about it. Okay, so how we logically think about something is very important. Okay, you need to use logic. Okay. Okay, so the key point here is one function doesn't affect the action of the other function. Okay, yeah, so you can commute. Okay? One function doesn't affect the map of the other mapping. Okay, it doesn't affect. So you can commute. So whenever you don't know the proof, right, go back, convince yourself using example, and then come back. Okay, not just example. You need to support with argument. Okay, yeah. Use example to see proof. This is how we learn proof. Okay, not just through by this alphabet. This alphabet means some numbers. Okay, so second statement I gave you last time was any cycle, okay, in S2 and above can be written as the product of transposition. Okay, and last time I gave you a formula, right? So, and I have reminded you just now. So let's say we have n cycle. What can we do? We can break it by inserting all the middle term. Okay, for example, A1, A2, then A2, A3, and then so on. Okay, but this is not the only way you can do it. Okay, not the only way you can break into product of transposition. You also can do it this way: A1, AN, and then A1, AN minus 1, and then A1, A3, and then A1, A2. So basically, you start from A1 and then go to last one, and then start from A1 again, go to the second last one. It also works. Okay, so let's discuss. So the argument I want to write down is this is easily verified using function composition. Okay, let's see. Whenever we see this kind of word in the proving set, easily verify or check yourself or trivial, what does it mean? Okay, what does it mean by this? So by checking the position. Okay, let's try go through this kind of argument. Why people will say this is easy. Okay, so look at the left-hand side. So it says that check through the function composition, right? So what happened to the left-hand side? Can you have the mapping inside your mind or not? A1 go to where? A2. A2 go to where? A3. A3 go to where? A4. Like that. Okay, subsequently. But if you look at the left-hand side, in particular, we check the first one first. Okay, what happened to A1? Does A1 appear anywhere or not, other than the first transposition? No, right? So this is the only transposition that control where A1 go. Remember, this is the only way that sending tell you where A1 gets sent. Where A1 gets sent. A2, but is there any function going to send A2 again? Anymore? No more, right? Nothing there already. So stop at A2 is the same. How about A2? Okay, if you don't believe, check again. How about A2? Which term will contain A2? Only the first two. But which one you encounter first? The right hand side one, A2, A3. So you need to do that first. So A2 gets sent to where? A3, but the next one got A3 or not? No. So stop at A3. So this is how this formula works. Okay, no. You can go to the next one and argue. Okay. If you really want to prove it, okay, you can use what? Induction. Yeah. Because you need to prove for all and yeah. So you can see that I show you base case true already. Okay, then you assume inductive hypothesis and then you do the inductive step. Okay or not? Okay. How about this one? This one, second one. How about second one? So does second one send A1 to A2 or not? Like Lydia, why? So all of them has A1, right? But you need to see the first spot that having A1 first. But the first spot send A1 to where? A2. But any A2 appearing or not? No more. So A1 stop at go to A3. And then you argue about A2, right? About A2, what happened to A2? A2 gets sent to A1. But the next one still got A1 or A1 gets sent to A3. But any more A3 or not? No more. Then stop at A3. So you can imagine or not that train, the train, both TRAIN and TREND, train. You need to imagine the train. Okay. 不止花样，那个火车你都要想象。有那个火车路有看到吗？没有。有。Sorry, MRT, LRT also can. 新竹谷新干线 also can. 日本的火车。Anything, okay? So anything you can imagine. So you need to, for mathematics, you cannot just see number, alphabet. You need to see these picture, these movement, this symmetry. Only these number will come alive in your mind. Okay, no? Yeah, you need to use your own way, use your own way to think. Okay, try and develop your own way. But make sure your way is correct. So you need to always check with me, check with the people. Okay, so actually, I think in Jackson exercise, right, there are more ways. I think there are 2 more ways or 1 more way to break into a transposition. You can try and prove it. Okay, there's 1 more formula. Okay, good. So this one done. So if you really want to write it down rigorously, so you need to use induction. Okay, so the last one is a bit hard, a bit tedious. What's the last one? This statement here is very, very important. Okay, it's a very important statement inside symmetric group. Namely, if you have a product of an even permutation or odd permutation, transposition, just transposition, then any other way of writing down it as a product of transpositions will be also even or odd. Okay, it will stay. If it is even permutation, it will stay as even permutation. If it is odd permutation, it will stay at odd permutation. So do you know why this theorem comes after the theorem says that every cycles can be written as a product of transposition or not? You know why? Do you know why? You know why it comes after that theorem? So you need to ask yourself, what's this theorem talking about? This theorem is talking about product of transposition. Okay. So if you don't know that whether your element can be written as product of transition or not, this statement here almost useless. But once you know that every cycle in the symmetric group can be written as a product of transposition, then you can ask about how many transpositions represent my element in Sn. It turns out that if there's one way to write it down as an even number product of transposition, then all other way you try to break it is still even. If it can be written as odd number of permutation, it will stay odd again. Never even one. If you don't believe, go back and try. Okay? Go back and try. For example, what? Okay, I need to give you example. You need to keep some example in your mind. What kind of even permutation or permutation? For example, what? For example, you already saw an even permutation, right? 1, 2, 3. Okay. And you can consider the other odd one. What kind of odd one? Just add one more. So by the formula just now, do you know what you get? 1, 2, 3, 4. Okay. So can you imagine what are the other even permutation way to write 1, 2, 3 or not? The cycle 1, 2, 3. Can you imagine? Sorry? Try. Must try, eh? Good. This one is the formula we gave just now, right? 1, 3, 1, 2, right? And then I think there's another one is 2, 3, 1, 3. Okay. Any other? Oh, a lot. God, a lot. Infinitely many ways. You can just simply put 1, 2, 1, 2 at the side. They compose to identity. Okay, maybe it's trivial, but it's one possible way. Okay or not? So you can add a lot of identity. Okay. Brilliant of identity. Okay, so similarly for the odd case. Right. Okay, we will finish this proof before we take a break. Okay. So before proving this, right, we need a lemma. Okay. What do you think when you heard about lemma, the word lemma? What do you think? What do you think when you heard about lemma, this word? Do you feel good or bad? Bad. Why? Good. Why good? Yeah, make something easier. This is the point of lemma. You prove something, the intermediate step first, okay, and then you can use this lemma. So in this case, we left hard stuff to the last, no? So we use this lemma first. Okay, see how this lemma work. 有用的话，我们再 prove 它；没有用的话，我们就把它丢了，好不好？ So we first see if this lemma is useful or not. If it is useful, then we will prove it. Okay, let's see how to use this. So what does this lemma say? If the identity is written as a product of R transposition, so meaning what? You split your identity into R transposition. Then you want to show that R is an even number. Does this lemma make sense or not? Make sense or not? Does it make sense? Just now how we create identity. 1, 2 times 1, 2, right? So there are even number of them. So it says that the only way to write identity into R product of transposition is even number. They must always have a transposition cancelling. Okay. Okay, boss, okay. Okay, so right. So before we prove this, let's see how we use this first. So how we're gonna use this to prove the statement here. Okay, how we're gonna use this. Okay, let's see. Okay, let's see. So proof. So there are two cases to prove, right? So in the when you see a theorem, first thing is to understand. Second, you need to ask yourself what to prove. If you cannot understand this question, don't bother reading the proof. No use. Okay, you need to understand the segment first. Okay, so actually there's a hidden two statement here. Can you read it or not? There are two cases to prove. One, even have to written as even. Second, odd have to written as odd. Okay, so we prove case by case. So we start with even permutation. So let's use proof first. Let's use this MR first. Theorem. Fine. So we first prove the case of even permutation. Okay. So what do? So obviously the assumption start with sigma can be written as a product of even permutation. Okay. Where M is even. Second, what do you need to show? If you can write sigma as another product of transposition, you want to prove that that number of transposition is also even. Okay, so suppose sigma equal to sigma, and also suppose sigma equals to, let's say, tau 1, tau 2, out to tau n, such that, and not such that, yeah, such that what? Such that all these sigma i's and tau i's are transposition. Okay, so what do you want to prove now? 来，潘星 what do you want to prove now? 学 proof 不可以只是跟哦，你要 actively involve， 你才知道在干嘛。错不用紧，但是你要 actively involve， 一直听下去是不会想到。Okay, so what do you want to show here? Want to show that n is even. Good. 干嘛？会打架在班上。Okay, so we want to show that n is even. Okay, so what do? We know about identity. We know about identity. Can we use the fact we know about identity here? Can you make an identity out of sigma or not? Can or not? Or let me ask you a question. Is sigma invertible or not? Yes or sigma is invertible. Why? Because symmetric group is a group. Okay. Obviously, because we call it a group. So not that E is sigma inverse. So what are you gonna do here? What are you gonna do here? And we have two ways to expressing this sigma, right? Okay. We have two ways to express this sigma. So how are we gonna play? 来，潘星，给你玩一玩。就是不会，不会，你抬在这里吗？你会啊，你来这边做么？来，玩一下，哪一个？你 which one？有两个等于。Okay, maybe try the first one. Substitute 啊。Okay, and then 还要用第一个吗？再要不要？这么你知道不要？If you're gonna place the first substitution again, right? What happened? Yeah, 就没有了，什么都没有，都没有用。Okay, so good, very good. So this is your intuition. Okay, so you need to develop your intuition. Okay, so maybe we want to use the second substitution here. Okay. But what is this? What is this compose inverse? 哇，老师没有教，不会了，都惨了。Think again. What are these sigma? They are function, right? If you compose a function taking inverse, how to compute? FG inverse is what? G inverse compose F inverse. So you need to invert F and G, right? So similarly here, so you will get sigma inverse, sigma 2 inverse, all the way up to sigma n inverse. Do we use n on n? Okay, sorry. Okay, it's n. So what do you note? What is sigma inverse? Sigma 1 inverse, what is it? Sigma n inverse. Sigma is what? These are transposition. Who are the inverses of transposition? For example, 1, 2 lah. Think about 1, 2. Who's the inverse for 1, 2? Except, right? You swap 1, 2. You want to do identity, you need to swap it back. You do 1, 2 again. Okay, so all these sigma I inverse is just sigma itself. Okay, no? Okay, no? Okay, transposition is what? Swapping two number. If you want to swap it back, you just need to swap the 2 back. It's again the same thing. 2, 1, 1, 2 is the same cycle, right? Yeah. Okay. So, but lemma says what? If you can express E as a product of transposition, this number of product has to be even. So meaning what? By the lemma before, how many of them here? How many transposition here? M plus N must be even. Have we reached our goal yet? What do we want? 做这样久了，好像忘记了，刚才要做什么了。N is even. But what do we know about M? M is also even. M is even and M plus N is even, meaning what? N must be even. Know how to prove or not? Use number theory. Okay. Yeah, maybe we can add this into chapter 0. Yeah. So similarly, you can use this argument for similar argument for odd permutation. Okay, try and practice. Okay, try and do it for odd permutation. Okay, no, try and do this. Be applied to prove the case of odd permutation. Okay, try and write it out yourself. It's the same argument. Okay, no. Any question? Okay, if you don't understand this proof, go back, write for the odd first. See you can reproduce this proof or not. All right, so this lemma is pretty useful. So I want to go through this lemma because when during that proof, there's some technicality that you need to know so that you know how to compute product of transposition. Okay, so let's prove the lemma now. So let's bring the lemma with us. Yes. Yeah. So now we're gonna prove this lemma. Is this lemma really true or not? Okay, so how are we gonna prove this? So this R, right? This R is a random R. Okay, it's a random R. So we will use induction on R. Okay, we will use induction on R. And then prove that this R has to be even. Right. So R can be 1 or not? Can R be 1? No, right? Because a transposition cannot be the identity. Because if you do one transposition, you will always swap 2 indexes. Cannot be identity. Okay, so this R here, right, must be greater than, at least greater than 1. Okay. But what happens if R equals to 2? If you already can write E equals to T1 equals to T2, then We are done. Correct or not? Why we are done? Because 2 is even. Does it make sense? Need to remember our goal to show R is even. If you can write it in that way, then that R have to be even. So when R equals to 2, obvious. In fact, you know more, right? T1 has to be equal to T2 if you can write in that form. Okay, so the assumption is you need to write in this form first. 前提是你要这样子可以写这个等于，不要考虑那种 1, 2, 3, 4. You cannot consider 1, 2, 3, 4 because it is not identity. So if you ever can write it down, there must be actually T1 has to be equal to T2. They are inverses of sharing. Okay. So how about general R? So for let's say, suppose now that R greater than 2. Okay, so what happened if R greater than 2? Maybe you have 3 transposition, 4 transposition, 5 transposition, 6 transposition, 7 transposition, 8 transposition, for example. So in this case, you start with 3, 4, 5, 6, 7, 8, right? So you can look at the first 2. Okay, actually look at the first 2. Okay, in this case, you look at the how to say first and last. How should we read these things? Should we follow the convention of function, or should we follow the cycle or the? Okay, so let me ask you a question. 1, 2, 3, 4, and 4, 5, right? Okay. So where is first? First is 1, 2, or first is 4, 5? 4, 5. You want to read in this way? Yes. Yes. Okay, let's fix this notation for this class. Okay, let's fix this convention. Okay. So in this case, right? Consider in this case, consider the product of the first. So let's keep our convention here. So this one is first. The first 2 transposition. But a bit weird though, because when we order, right, we order as TR minus 1 and TR. I think we should call it last better, right? Due to this ordering. Because our order is going from a bit unfortunate in this course, because when we order this product, right, we order from the left to right. But when we do the product, actually we do it from right to left. So you need to be careful about this. Be careful about this. So due to this R, right, I think it's better we call it the last. Okay, we call it the last. Due to this order. Okay, so say the last 2 one. Okay, but anyway, what I want to say is we consider the last transposition or the first 2 function. Okay, use a different word. So let's consider these 2, TR minus 1 and TR. So what could it be? Can you imagine what happened? So this 2, right, could be AB, AB. Are there any other possibility or not for this 2 transposition? Other than AB, AB. This is what we have discussed before, right? What kind of composition can happen between these 2 transpositions? Can you imagine? Sorry? AB what? A, B, C, D. Okay, maybe all of them are different. A, B, C, D. Okay. If maybe all of them are different, and then what sort of possibility could happen? A, B, A, C. Good. A, B, A, C. What else? Wait. Remember, these A, B, C are just number, right? So imagine you got 1, 2, 1, 2, right? What else you could have? Maybe 1, 2, 3, 4. Right or not? What else? Maybe 1, 2, 1, 3, for example. Any other possibility could happen or not? AB BC. Okay, AB BC. Yeah. Okay. You can list out more, and then I think they will reduce to these 4 cases. And the rest will reduce to these 4 cases. You can list out more, but they will reduce to these 4 cases. What? Question? Ask now. You better ask now. Better ask now. Why what? Huh? Oh, I mean, so I'll give you a general product, right? So you want to look at the last two, what's the general, like, what's the pattern you can get from these two transposition? 听不懂? I mean, either 有可能性，有可能吗？没有可能吗？有可能，可能罢了。We need to consider all the possibility. All the possibility. Okay. The question is very easy. Okay. What are the possibility of taking product of two transposition? 有多少种类的 transposition 可以两两相乘？ Sorry? 第三种和第四种 This one, these two. Okay, so maybe we can try one example. Maybe we try example. So let's try example. So if let's say what? Let's say this one is AB, AC, right? Okay, so if AB, BC is what? AB is 1, 2, BC is 2, 3. Right or not? Okay, so are they the same or not? Let's see from example first. Okay. Are they the same? So this one 1 to 2, 2 to 1, 1 to 3, 3 to 1. This one 1 to 2, 2 to 3, 3 to 2, 2 to 1. So they shouldn't be the same. No, I mean you can prove it generally. Instead, you can prove it generally. You should prove it generally. Prove it generally if you don't believe. Yeah, prove it generally. Yeah. Prove it generally. Yes. A, B, C. Yeah. A must be A, B must be B, C must be C. Say again. What do you mean by stop there? Oh. A must be A, B must be C must be C, that's all. A must be A, B must be B, C must be C, that's all. That's all. Different, right? See this example here. So you need to prove it generally. You can prove it generally. Prove it in general. Where this guy send A to? Where this guy send A to? Just check. This guy send A to B. Right. This guy let's send A to B, but B sent to C. So A gets sent to C, this guy. So different already. They're already different than A. Make sense or not? Make sense. Must make sense. Either you wrong, either I wrong. I wrong is okay one. But make sure it makes sense. 来，快点，不要浪费时间。哎呀，不然你问，我快点，不要害羞。我还没有做东西，我只是讲有这4个东西吧。喂，没有问一个很简单的问题啊，问一个很简单问题吧。拿2个 transposition 相乘有什么 possibility？ 这2个 transposition 可以有多少的可能性？我没有讲一定，这4个都有可能，4个都有可能。 可以 OK 啊，BCBC OK 啊，但是这个 A 跟这个 OK，this is the main problem here 啊。喂，excuse me，sorry，没有像你，我没有像你啊，这个是很严肃的问题，真的很严重的问题。这个不要笑，这个是真的很严重的问题，不是很严重，是很严肃的问题。OK，it could be BCBC, but we regard that these two are the same case. Why is it same case? Because I can map B to A and then map C to B. Okay. Okay. Without looking at these three, can you recognize that these two have the same pattern? What's the pattern here? The pattern here is I repeat the first two index again. Same pattern. But within this language here, A, B, C should be different. Okay or not? You need to memorize the relative position. Relative position is very important. 明白吗 ？OK or not? Pattern，我可以把这整组换掉，可能这个叫 BC，这个叫 BC，这个叫什么 ？EF， 对，没有错，推得出吗？如果你推得出 pattern 就在了，因为什么 ？OK，so let me tell you what the pattern 啊。First one repeat pattern. Second, I make disjoint cycle. Okay, let me write down. Oh, this one is a repeat. This one is a disjoint cycle. Okay, and then the next one, next one, how to call it? Huh? I also don't know how to call it. So the next one, how to call it? You change B to C, change the second one to C. And then the third one, you change. Okay, so the first one you change. Okay, I know how to write it. So this one you change second index to C. So the reference point is AB. Reference point is AB. Okay, we keep AB. And then the 1, 2, 3, 4. So the 4 one is to change. Okay, so don't say second, just say change B to C. And then the fourth one will change A to C, like that. So the claim, okay, this is the important claim. If you try to write out all other combination, they will reduce to these four patterns. This is the claim. This is 很严重的控告，要 proof 的。所以你要控告一个人的时候，你要 proof。有问题吗？还有问题吗？哪一个还要选吗 ？OK， 再选一个 ADAB 是吗 ？ADAB 哈 ，ADAB 是不是 ？OK。So let me ask you a question. ADAB same with which pattern? Third pattern. Why? Because we changed B to something else. Yeah. Okay, if you don't like C, maybe say something else. Something else. Okay, I think this one better. Yeah. Something else can E, F, G, Z also can. Okay or not? Happy, yeah? Okay, but the important claim is why only reduced to these four cases is quite argument. Okay, so should we take a break? Yeah. Attendance first. Yeah. Okay. So I will. Let's take a break. Let's take a break, and then I will take attendance during the break. So let's break until 6:23. OK，会帮你筛。Okay, those who go to toilet later, I will call you again. Don't worry. Sorry. Okay. Okay. 小康，你不在。小杨，小杨，林红杰，林红杰，林红杰那边，林红杰，卢子明，Yep，曾子航，Adrian 在，嘉玲，参嘉玲，I see，也还有一个嘉玲啊。哦，OK，卢子璇，卢子轩，卢子轩，Yeah，嘉玲子轩，莉莉亚，哦，还有一个嘉玲，OK，很好。E 少 K 有 Eugene。Jasmine, Albert, Albert. I think I saw Albert just now. Albert. 包成 B. 超金玉，超金玉。恩浩瑞去哪里？OK，在吗？陈之浩，陈之浩，戴一琛，何心怡，修彤，李冰夏，刘晓月，刘晓月，刘晓月，刘子涵，刘子涵，上厕所 OK。罗红瑞哥，马宇轩，孙佳怡，孙佳怡，佳怡，王芳宇，哎，孙佳怡没有，王佳怡呢？OK，王舒瑶，吴雨熙，谢长云，严胜，姚逸晨，一凡，钟一凡，I see，好，若星，Where's 若星？Yeah，OK，right，赵胜，洪赵胜，MAT211 昊天金星，李金星，OK，林一航，修哲，OK，瑞刷康星林恩，Where's 林恩？Ian 郑月，赵瑞，Where's 赵瑞？厕所啊，OK，刘金鹏，韦泽诺here 啊，林晶，OK。Okay, so can I have Chang Yun here? You come here, come here, come to the front. Xing Yi, where's Xing Yi? Xing Yi. Yeah, please come to the front. Ling Eng, you come here. Chen Bi, not Chen Bi. Ian, you come here. My extension. Have you messaged me? Not yet. Teams. Yeah, or email me. How about Seng? Have you submitted your assignment yet? You not yesterday the due date?
好，你不是延迟到那个
哦，
你不延期
没有，那个延期 ，Did you read my？
不是作业上面写着的吗？对啊，
我知道。
我以为延期还没交。
No，等一下，你冷静，冷静。看我的 announcement 吗？你们有看不？
你看，我只看了作业上。
看一下，这个是10月1号啊，是星期几？就是那天我们上完课哦。所以说，如果你需要那个 extension，你要 message 或者 email 我，告诉我。
是说啊，我还以为是作业上写的，我就直接没交。
对，没有，你不可以以为，有时候我在班上会报告。
那我已经写完了，我现在交了。
晚上
回去交。
你晚上回去交。
还有什么事拍
啊？
还有什么事？
暂时没有。
好 ，OK。
暂时。晚上。你晚上讲。OK， 好。啊，滑下去。会跟我讲话吗？你讲讲看。什么意思？那4个 case 啊？这一个要有一点 argue 吗？要 argue。就这4个是所有的可能性啊。证明哦。
More example you try.
不然你 try， 你要有一个证明。你4个号码嘛，4个号码可以放什么可能性？4个都一样嘛，不可能4个都一样的吗？不是 bijection， 只能够两个一样。OK。2个 transposition 里面有4个号码。对，然后1的什么情况？我知道，对。OK， 你要一步一步哈。假设有4个数字嘛，2个 transposition。OK， 这2个 transposition 里面的2个数字不可以重复了。transposition 吗？不可以重复。对呀。没有意义这个东西啊，没有22这个东西。会重复。第一 ，OK， 你看到这里全部都没有都不一样。这样你就考虑 combination， 就是 combinatorics 哦。这样考虑组合，对，有怎么样的组合嘛？有什么？你就要考虑完所有的组合方式，然后 turns out that 就有4种。有一个我讲解释的问题。等一下我看看几点。OK， 可能要 start 先。Hello， 肯定。刘小月 here 吗？刘小月。OK。孙佳怡呢？刘金鹏 OK， good. So, those who have these lecture note, trying to type the lecture note, right, we will meet after this lecture. Okay, after this lecture, we will have a meeting. I think Ziming asked about it, right? Where's Ziming? Still can't recognize. Okay, Ziming. After lecture. Okay, so we will continue this proof here. So, 潘星很怕啊，为什么只有这4个？So you need to consider all the combination. Okay, you need to consider all the combination. So it's a combinatorics argument here. Okay, combinatorics argument here. If you want to know why there are 4, it's only. Okay, all cases will reduce to these 4 patterns here. Obviously, first of all, you need to show that they are different first. Okay, just now we somewhat argue that there are different, right? But why are these the only 4? Then that's the other argument. Okay, but we won't do it now. Okay, so these 4 cases happen. What we can do with these 4 cases? If one happen, what happened? What happened to AB? There, cancel. So meaning we can cancel 2 of these from the original product. They become identity already. Okay. So you can do it. But if we already reduce to less than R, right? Meaning what? By induction, R minus 2 has to be even. Okay, we can apply inductive hypothesis. R minus 2 is even. But if R minus 2 is even, meaning what? R is even because you just remove 2 of them away. You add 2 back, it's still even. Okay. So if the last 2 is this, then we are good. But how about for all the other cases? They don't cancel. ABCD won't cancel one. ABAC also won't cancel. ABBC also won't cancel. Okay, so what to do? 死啊 all you 把书盖起来睡觉了。We must do something. Okay, because this lemma is correct. So what to do here? So what we can do is we slide AB across. Okay, how do we slide AB across? So for the rest, what happened? So let's write down for the rest. How do we slide AB? So we have CDAB, right? CDAB, and then SC what? AB, and then what? BC, A, B. Okay, we can try and slide AB across. Just now we use AB to cancel, right? So now we try and cancel this AB with other AB. Okay, let's try. So for the first case, we can, since it cannot cancel with CD, right? We need to hope that it can cancel with the other AB. So we move it to the front. Okay, we can simply move it. Why? Because these are the product of disjoint cycle. Okay, I can just move it front. Second, how to move it front? If we move it front, what we get is AB, BC. Remember the formula we have just now? But the last one, maybe you want to think that I want to do AB, AC. But this is not what we're gonna do. Okay, we're gonna do instead we're gonna do AB, BC. You know why? Okay, I purposely leave the A on the second last transposition. Okay, I want to leave everything that we move to the back is nothing related to A. Purposely. Okay, we do it purposely. Later we will have an argument on this. Okay, we purposely do this. These 2 are okay, but I don't choose this. Okay, we don't choose this because later we will do an argument on AB or A. Yeah, AB. Yeah, don't do this. Don't do by choice. Okay, it's correct, but I don't want that choice. So what happened? If because we start with what? R greater than 2, right? r greater than 2. Meaning what? Meaning we have an extra one at least. Okay, extra one. So what's the possibility? Either A, B get cancelled again. If A, B get cancelled, you can use the inductive hypothesis again. If not get cancelled, what happen? Keep moving. Using this three-way, move only. Move them all the way up to the first one. Can or not? Does it make sense? 火车，火车，小火车。火车。Use this to move AB. There are three ways to move AB. Right or not? If you meet the first case, what happened? AB get cancelled. Okay. If it doesn't get cancelled, you keep moving AB until you move to the first one. Question? No question? Can you imagine what I say or not? Can you imagine? No? Where you lost? Later I will tell you. Move first. Do you know how to move first? Before I tell you why, you need to know how to move first. Later I will tell you why I move it. Do you understand how to move? No, right? Because there are only 4 possibilities you need to remember when 2 transpositions meet together. This is what I claimed just now. Only 4 types. First type, what happened? AB will meet with AB. Then they cancel. If they cancel, you can go through the first argument here. Then use inductive hypothesis. Yes, good question. Does anyone know why I can say r minus 2 is even or not? By inductive hypothesis. So what is the inductive hypothesis you need to know? So what's the statement you want to prove? 全部都不知道 then 就不用 prove 了咯。因为you have to remember what's the statement you want to prove. If I can write E as a product of R number of transposition, then R must be even. But by inductive hypothesis means what? I suppose everything less than the product of everything less than R is even. This is the inductive hypothesis. 明白吗? Assume that any product that is less than R, it is even. 这个是 inductive R. 这个很重要 inductive 那个 proof. Inductive proof 是在讲作用啊。我 assume 一个比较小的号码是对的先，我 prove 它下一个是对的。怎么 prove 下一个是对的？我要用我知道它在小的 case 的时候都对，明白吗？ So in this case, I want to prove that R is even. So everything less than R should be true. Okay, so I can use the statement. Okay, 这个是 about inductive proof. Okay, if you don't understand, need to think about it. Cannot explain now. Okay, but you need to know. Go back and understand inductive proof first. Okay, and then so what can you do? If your AB cannot cancel, you left with 3 cases here, right? And then I demonstrate that I can move AB forward. Okay, yes. 现在又算错了，算错了，等一下，应该是 AC 哈。Yeah, AC. Thank you. Yeah, so AC, good. So we move the transposition containing A forward. Okay, later I'll tell you why. Okay, I'll tell you why. So does everyone agree that I can move transposition containing A forward? As long as it doesn't get cancelled, I can keep moving it until the first one. Okay, if it cancel in the middle, we go back to the first case. Okay, if it cancel, we go back to the first case. So the worst case is I can keep moving it until I move to the first one. Okay, now the real argument comes. The new argument, real argument comes. So if the transposition A to something, you see that maybe it's AB, maybe it's AC. Okay, if this transposition doesn't cancel with any middle term of transposition, we can move it all the way to the first one. Okay, I can move it all the way to the first one. If we cancel that, what happened? Then we go back to the first case. Okay, use inductive hypothesis and then imply that R is. Okay, so if it cancel with, if it cancel with the one of the middle term, then we go back to first case. Okay, so what happened if I move all the way to the first one, I'll go something A to the something, but the rest, there's nothing. Sorry, is it okay? So for the rest, there's nothing about A. What happened? This implies what? It's not a what? Not quite. Not an identity. Because the first transposition must move A somewhere else. And then there's no way to move it back. Because that's the first transposition. Okay. Okay. However, so I'll put here, however, it cannot happen. Cannot happen. As, in other words, we said that the identity would not fix A now. Okay, would not fix A now. Okay. So what? So meaning I cannot always move it to the first one, no, it must get cancelled somewhere else. Okay, so therefore the transposition, A something, when you move it along the way, it must get cancelled somewhere in the middle. B, cancel off. And you commute it. Don't use commute. When you how to say this? What's this action? When you move it forward. Must be cancelled where? In the middle. Or cancel with the middle transposition. Okay, when you move it forward. Okay, if it cancel, then you happy again, no? You go back to the first case. Then the identity must be the product R-2 transposition. Okay, so we go back to the first case, then we are done. Okay, and we are done. Okay. Okay, no. Any question? Different question? Different question. The whole thing. Yeah, the whole thing you don't understand, right? Go back to the statement again. Repeat the statement. Can you repeat or not? If you cannot repeat, read again. Read until you can repeat the statement, then only you go to proof. Otherwise, you cannot straight away go to proof one. It's useless. You need to understand the statement first. Maybe you need to use your own word to state the statement first, if that's a better way. But you need to remember a statement. Otherwise, you cannot just follow proof one. You will get lost. Because proof is quite personal sometimes. You know, actually almost always is personal because you will have different idea. So maybe you have your own idea of solving, but the problem now is you need to learn people's idea. Okay, you need to listen to what people say. This is what mathematics really do. You need to learn to listen to people's idea. If it is wrong, can you give counterexample or not? If it is true, can you prove it yourself or not? Okay, you need to listen to people's idea. Maybe you look at Ardina, you look at Jackson, you look at Frale, maybe the same statement they will write a little bit different proof. So do you understand what they say or not? OK，不懂不用紧，再来试罢了，一定懂的，人家都懂了，那可能不懂，是不是？都有人懂了，是不是？大把人在外面都懂了，是不是？这里就有一个懂了，是不是？所以一定懂的，再看吧，再看，再看。OK，this is the process. I would say this is a process you have to go through. OK, I cannot fast track you. You have to go through this process. 这个痛苦的过程是很重要的。So you need to go through this process. Any quick question or not? Any quick question? Yes. Identity will not fix A, meaning identity have to fix every indexes. Correct or not? But if you ever move transposition to the first one, okay, but we know that identity is equals to, let's say, where is it? Where's the fifth one? So identity we suppose, okay. By assumption, what do we have in our mind? We have that identity is equals to A to something, blah, 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 blah. We have moved A something transposition, move to the front already. But you see, this A must send, this transposition, this first transposition must send A to somewhere else. So it never fix A anymore. In this case, in this assumption, under this assumption. So this is the contradiction here. Because identity must fix everything. You mean the result of this proof? Not cancel. I mean, oh, you mean, okay, you mean the result of this proof is it? If you can write it as a product of transposition, then there must be a way such that those transposition cancel. Yes, that's right. True. You can imagine or not? Okay, maybe I give you some imagination. Maybe I can write 1, 2, 1, 2 like this. I can write differently, you know. I can write 1, 2, 3, 4, 3, 4, 1, 2 also can. What else I can do? I can do weird stuff 1, 2, 2, 3, and then 2, 3, 1, 2. I can also do even weirder stuff. 1, 2, 2, 3, 1, 2, 1, 3. All these are identity. Can you verify that? When you try to verify all these different examples, you will appreciate this proof. This is how we do maths. We look at all the possibility, and then we make a conclusion. 我们总结，看完所有的情况，那我们做总结，就有这4种可能性你要 consider 的，然后我们抓到那个症结点。Okay, we find the most important key point. Okay, if we ever can move some transposition to the front, then we won't have fixing the indexes. Okay. This is the first long proof you see here. Okay. This one need to train one. Need to train. I need to train. It's like you go to gym. You need to take 5 kilo, 10 kilo, 15 kilo, and then until you get 100 kilo, 200 kilo, then you can go Olympic. Yeah, so you need to slowly, okay, add your brain strength. Okay. What time is it? Wow. Let me see what else I need to say. Okay, so let's finish subgroup before we go back, okay? Finish subgroup before we go back. So we will have one definition and then a definition of subgroup, then we can finish. Okay. So by this theorem here, what can we define? We can define a sign. I think this is important for your assignment. Sign of an cycle. Okay. In Sn is +1. Okay. If it can be written as even number of permutation. Not permutation, but 2 cycle, okay, transposition. And we define it to be -1 if it can be expressed as an odd number of transposition. Okay, let's give some examples. So for examples, what's the sign of transposition 1, 2? +1 or -1? -1, right? Because it's odd. Okay. How about the sign of 1, 2, 3? +1. Why? Because I can write 1, 2, 3 as 1, 2 times 2, 3. So it is written as the product of even permutation. So it's sign of identity +1, because by the lemma we show that it is always be an even permutation. Okay. So I tell you more advanced stuff. So we will say that so the moral here, maybe put more. So what's the moral here? Moral of the story. So this sign, right? Sign of the sign of cycle, n cycle is an invariant. Okay, it's an invariant. Yeah, I will explain at the moment. Yeah, so it's an invariant on a symmetric group. Okay, so invariant in your mind is what? Something cannot change, but under what it doesn't change. Okay, it doesn't change under the presentation of your n cycle. Remember, it doesn't change under the presentation of the n cycle. What does it mean? Maybe I can have different way of writing 1, 2, 3, but it will always compute to the same sign with the cycle 1, 2, 3. Do you believe or not? Why? Why? First of all, so the logic line is like this. First of all, an n cycle, you can write it as a product of transposition. Okay? So if it's in the product of transposition, you can count how many, right? But we prove a theorem says what? If you can write the sigma as an even number of permutation, all other way writing that sigma is still an even number. So no matter how you express this 1, 2, 3 in terms of product of transposition, it will always be even. So if it is always even under this definition, you get what? You always get 1. Okay. Yeah. So this is what this invariant means. Okay. No? Invariant under the expression of cycle. Okay. 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 So we've done this, and then there's one more way to think about this symmetric group. So let's try this way. I think this way is also important for your assignment. So there's another equivalent way to formulate a symmetric group. So in this case here, I want to pull out your linear algebra. 听了都头痛是吗？OK， 不要头痛，不要痛，不要痛。来 ，Let's see 啊。So how do we think about this linear algebra here? So we try and attach each index, let's say 1, 2, up to n. Okay. Who do we attach to? In linear algebra, there's one object you really have to know. This is called the standard basis. Standard basis is very important, no? E1, E2 up to En. How that looks like? How do they define? E1 is 1, 0, 0, 0, 0, 0, n minus 1 of them. E2, 0 at which place? Second place. 0, 1, 0, 0 all the way like that. Okay, so the subscript n will tell you where the 1 have to be. And then all the other entries are 0. So these are the standard basis. There are very nice properties about these standard basis, but we don't need now. So if we attach these, then the claim is the cycles in Sn simply corresponds to the permutation matrix. Have you guys learned permutation matrix or not? No. Of course not. Permutation matrix? No. Permutation matrix? No. What's the definition of permutation matrix? The permutation matrix definition. Don't know. 没有上，没有听过，没有听过，大的有。Let me see. What's the permutation matrix? Never mind. We recall. So what's the permutation matrix? So permutation matrix is defined to be an n by n matrix such that every entry and every row, such that every row and every column has exactly 1, 1. So it is like identity matrix, but you can permute it. Once you permute it, actually it also do permutation also. What it permutes? It permutes the standard basis. You want to try? I give you some example first so that you know what is going on. So for example, what kind of permutation matrix? Let's do it 2 by 2 easy 2 by 2. Okay, easy 2 by 2, what can you do? Obviously, identity matrix is exactly 1 in 1 row, 1 in 1 column. But there's another way to do this permutation matrix. Yes, you can do 0, 1, 1, 0. So what can you see? If you take 0, 1, 1, 0, what happened to the, let's say, E1? What happened to E1? You can do matrix multiplication or not? Hopefully you can. Because we have done it in your assignment 1. Yeah, you send E1 to E2. What happened to E2? You send E2 to E1. What is this doing? You are swapping. So if you go through this relation between 1 and E1, 2 and E2, you can see that the map, so under the bijection, we see that. You see what do we see? The permutation 1, 2 correspond to the matrix 0, 1, 1, 0. Piano. Okay. But I claim that this one is easier to compute. Do you think so? This is just matrix multiplication. But the cycle, you need to jump. But this one is just multiplication, matrix multiplication, linear algebra. Row column. Yeah, no? So maybe you can ask a question, whether number is easy or vector space is easier for linear algebra. Which one is easier to compute? Which one is easier for computer, for example, to program into computer? AI is using matrices. Yeah. Okay. But actually, this one has a deeper meaning. When we do this, when we associate number to vector space, this is one very frontier idea, what we call as a categorification. We categorify the set of numbers. Yeah. Categorification. We put a space on top of number. Okay. We don't just consider number, we consider number as a space. Okay. Yeah, this thing is important for your assignment, by the way. Okay. So we still have 6 minutes. So let's finish up our subgroup definition, also important for your assignment. So definition. A subset H of a group G is a subgroup. Okay. If it has the following property here. Okay, it has the following property. So what property you had? So first of all, it must be closed. Okay. So last time we talked about when a subset is closed, right? So if A, B in H, then what? A, B must be in H. G, G not enough. I want to close in H. Okay. To be a subgroup. Okay, I want it to be a subgroup. And what else? I said this is a subgroup, right? Contain the word group or. So it has to satisfy the group property. You must have the identity. Okay. And then inverse. If anything in H, its inverse has to be exist in H also. Okay. So sometimes you will see the Arting solution, you will see like H less than equals to G. Okay, this classically they will write like this. So somehow they think of it like a number. So you now no longer live in a number world, you live in a spaces. But there's some, how to say, partial ordering there. Okay, partial ordering. Order as a subgroup. Okay, so you can think of a subgroup of a subgroup of a subgroup, and then the last one is a group. Like that. Okay, so there's a lot of questions you can ask about this definition. You can ask, hey, this identity is in H. G also has identity. Do they necessarily need to be the same? You can ask this question. If you do tutorial question, then you will know that there has to be the same. That's what you have to do. But to be a group, what else you need to satisfy? 3 things, right? What thing? Associative LC, identity, inverse. But not that here I didn't mention about associativity. So does it hold true or not? Yes. Some say yes. So why? So this is the question I asked in your assignment actually. This is what I asked for in that question. Okay, you need to prove if and only if, but the key point is why this subgroup definition has associativity. Okay. So I haven't finished. I will finish in the example with examples. Okay, so again, definition. So maybe I put a remark here. I put a remark here. So how about we'll finish with examples of subgroups. How about associativity? Okay, we want our subgroup to be a group. So next definition. A subgroup H of G is called proper. Okay, proper subgroup. So it's like a proper subset, but you have more structure. You can do LOC. Okay, proper subset is just said if H is less than equal to G. Sorry, just says that H is not equal to G because we know that it is already a subgroup. Okay, so in this case here, we will write H is strictly less than G. Okay, strictly less than. So there's one really important subgroup here. It's always exists in every group. You know what is it? Yes, the identity. Identity will satisfy the three property easily. E times E is what? The inverse of E is what? And then identity is E itself. It is everything. It satisfies all the property. Okay. So it will form a trivial subgroup. Okay, so when we ask about subgroup, usually if trivial subgroup satisfy it, we won't care too much. We only care about non-trivial subgroup. Okay. So a subgroup with the element E is called a trivial subgroup. Okay. And there's one very convenient I want to introduce. So I'll say that the group, okay, I put a, what's bracket is this? What's this bracket called? Vector bracket, man? I don't think so. What bracket is this? Anyone know what bracket is this? English? Anyone know what bracket is this? Suddenly I cannot recall. Triangle. Let's call it a triangle bracket first. Next time I search for you. Okay, if we have this triangle bracket and then with an element inside here, A1 up to AN, what do? We say that this group is the smallest, okay, smallest group generated by A1 up to AN, or the smallest subgroup generated by A1 up to AN in G, okay, such that G contains these elements. Okay, do you know what I mean by this? So you take G, okay, take this element in G, and then G will tell you how they compose. Okay, you compose them because in subgroup, how many property? Closure, identity, and inverse. So you need to make sure that this set here contains identity. Okay, let me write down roughly how this set looks like. So this set should contain what? So group is a set, so this set has to contain identity, first of all, and then closure. So meaning you need to take all the possible composition. Okay? Take all the possible composition. Like that, for example, blah blah blah. And then you need to take all their inverses. And then all their composition. Okay, such that it satisfies the definition of subgroup. And then this is called the smallest subgroup generated by this element. Does it make sense? Okay. No question? Question? Okay. Okay, such that. Okay, so let me show you how good is this notation is. Okay, let me show you how good is this notation. So let's go to this example. Okay, I will have let me see, 1, 2, 3, 4, 5 example, then we can finish. Very quick. Huh? So let's look at Z6. Okay, Z6. Okay, Z6. Yeah, Z6. So what kind of subgroup inside here? The first easiest one. Trivial subgroup. Okay, just put 0 inside here. Okay, use 0 to generate this group. What else form a group? So I claim the number 0, 2, 4 form a subgroup. Okay, can you see why is it true? Let's try. Let's try why is it true. Okay, let's try. So first of all, is it a subset or not? So is this set subset of Z6? Yes, right. Okay, what else you need to check? Closure, identity, inverse. Okay, but this set here should contain what? The inverse, correct or not? Because it's a smaller subgroup generated by this element. So you must have inverse, you must have inverses for 2 and 4. What's the inverse for 2 and 4? 4 and 2 again, actually. Correct or not? This one is equal to 2, this one equal to 4. Correct or not? It is the number that you add to it, you get 0. Okay, because if you look at this identity element, you should guess what is the LLC already. Okay, so it's just 2 and 4 again. Then next thing you need to take care is what? Subgroup definition, closure, identity, inverse. So closure, so you need to take all the possibility, the multiplication, the possible multiplication, correct or not? So what do? What can you do here? You can consider what is 0 plus 2, 0 plus 4, 2 plus 4. That's all I did. So what are these? These are 2, 4, 6, which is 0 again. So you go back to the same 3 number. Okay. Okay. So this is one of the example. And then what kind of subgroup you can see, for example, in R with multiplication, what sort of subgroup you can see here? Subset such that it is closed, such that it has identity, such that everything inside has inverses. Okay. What are the subset of R, for example? What? Sorry? Rational, maybe? Can you think whether 1 is in this rational with multiplication or not? Okay. But remember, this R is what? Always when you consider this multiplication, right, you need to remember that we take away 0 because 0 is not invertible, multiplicatively invertible. So similarly for this rational, we need to take away 0 when we consider multiplication. Okay. Is everyone there invertible? Just take 1 over it, right? Okay. And then what else? Is it close? If is rational multiply a rational number or not? Yeah. Okay, so it's close. Identity is 1. 1 is a rational number. Okay. So it is a subgroup. So we'll write like this. And then what else? We have how about complex number? Complex number is very interesting. So what can you consider here? Actually, you can consider something called the root of unity. Do you know what the root of unity is? Don't know. So let me write down the definition for you. So the root of unity is the solution. Okay, so maybe write like this: the root of s to the power n equals to 1. Okay, so what are these roots? So for example, e to the I 2 pi over n, e to the I 2 pi over n times 2. So these are the Euler formula, right, for the complex number. All the what, the Morpheus formula, all stuff, those stuff, right? Okay. So these are discrete, These are discrete, but we can take all of them actually. We can take union of them. Okay, we can take union of them. If I take union of them, do you know what I get? It's a very nice geometry here. So if we consider this a complex plane, so let's say this one is X, this one is IY. So UI, where UI stay, do you know? These are length 1 vector from the origin, right? Because s to the n equals 1 is the length is 1. So it circulate around the radius 1 circle. So if you take all of them, what you get? You get a circle of radius 1. Okay. Yeah, in topology we call this a S1. But anyway, yeah. So you get a circle of radius 1 in a complex plane. Radius 1. Center at the origin. Centered. Okay. 3 more, then we end. 3 more. 3 more. Third one. So what's the subgroup of Sn? Okay. We call it An. Okay. So what are these An? An are the what we call the set of even permutation. Just now we proved some property about even permutations, right? If you multiply two even permutation together, they will also be even. Okay, because every time you cancel, right, you need two of them to cancel. So you cancel 2 by 2, 2 by 2, 2 by 2. So it will stay even. Odd might not be. If you take an odd permutation, multiply an odd permutation, it might not stay as odd. Okay, so this group is what we call the alternating group. Okay, alternating group. Maybe if there's chance, then maybe we can discuss why is it called an alternating group. So you try and check. Okay, check that it satisfies a subgroup property. 3 subgroup property. 3 subgroup axiom. Maybe I jump this one. Last one. Okay, last one. Really last already. So GLN. Okay, inside GLN, we also have a subgroup, a very distinguished subgroup here, which we call a SLN. Okay, so what's this S represent? It is named as a special good, special linear good. How special is it? Very special. So special about what? So GLN tells you what? It's invertible. So by invertible matrix theorem, you know that invertible matrix has non-zero determinant. This group we also characterize by X determinant, where this determinant is equal to the special number you mustn't forget, which is 1. Okay, quickly, can you see why this set closed inside GLN? Why is it closed? Let's say if you take any two element with determinant 1, A, B, okay, multiply together. Why is it in SLN? To be in the SLN, what do you need to know? You need to check that the determinant of AB equals to 1. But what is determinant of AB? Good. Your LA is not bad. Correct or not? So what is this? 1 times 1 equals to 1. Okay? Yeah, good. Okay, so we will continue from a subgroup next time. Any question before we break? Oh, sorry, finish. So if you have joined our lecture notes typeset, so please stay back. Okay, so see you next week. Okay. 啊 ？OK， 去 swimming 哈，你们很多人去 swim 是不是？
是 training session
哦，free 的是不是？
compulsory 的，记得
哦，
啊，
别紧，去吧，没事，去吧，没事，去吧。